Corrosion, the destructive chemical or electrochemical reaction of a metal with its environment. Corrosion frequently leads to the failure of metal parts in service, or makes parts susceptible to failure by some other mechanism. Actually, corrosion should be defined as the undesired deterioration of metal, simply because if used properly, the process of corrosion can achieve very desirable effects. The standard electrical battery, for instance, functions by electrochemical action, the basic principle of corrosion. Corrosion, it seems, is a completely normal process. Corrosion is the normal, natural reaction of metals trying to revert to their natural condition as oxides or sulfides in ores, their condition of lowest energy level. In fact, when determining a corrective action for a corrosive situation, the first decision is whether or not the observed behavior is normal for the metal and its environment. The electrochemical nature of corrosion can be clearly seen when zinc is placed in dilute hydrochloric acid. A vigorous reaction occurs. The zinc is oxidized to zinc ions. Hydrogen ions in the hydrochloric acid are reduced to hydrogen gas. The hydrogen gas bubbles off as the zinc dissolves in the acid. Two reactions are involved: oxidation, which is anodic, at the anode, and reduction, which is cathodic, at the cathode. In nature, most corrosive reactions are not quite so violent, and the chemistry of the reaction is far more complex. What is important in the study of failure by corrosion is that corrosion can be retarded by reducing the rate of either reaction in the process. The two reactions, anodic and cathodic, are mutually dependent, and by reducing the rate of cathodic reaction, we automatically reduce the rate of the anodic reaction, and thus we reduce the corrosion. If the surface of the metal is coated with paint or other non-conducting film, the rate of the electrochemical reaction will be greatly reduced. Corrosion will be retarded. Certain metals show a passivity to these corrosive reactions. Passivity is the loss of chemical reactivity. Under particular environmental conditions, certain metals and alloys become passive. That is, they essentially become inert and act as if they were noble metals such as platinum and gold. Fortunately, the metals most susceptible to passivity are the common engineering and structural materials: iron, nickel, silicon, chromium, titanium, and alloys containing these metals. Passivity is due to the formation of a surface film or protective barrier on the metal. Stainless steel, for example, owes its corrosion-resistant properties to a very thin, transparent oxide film on the surface. In this case, the naturally occurring passive oxide film is usually enhanced with immersion in a nitric acid solution or steam. Therefore, stainless steel surgical implants develop this passive layer when the implants are sterilized in steam. The film is stable over a wide range of oxidizing power and is eventually destroyed in strong oxidizing solutions. Failures by corrosion. A number of interrelated factors contribute to failure by corrosion. The type of corrosion, the rate at which it proceeds, and the extent to which it progresses are all influenced by the nature of the environment and the nature of the metal surface in contact with the environment. Failure can also be influenced by the magnitude of the stress applied and its direction. These factors do not necessarily remain constant as corrosion progresses. They are affected by externally imposed changes and the changes resulting from the corrosion process itself. Other factors that greatly affect corrosion processes include temperature, temperature gradients at the interface between the metal and the environment, crevices in the metal part or assembly, relative motion between the environment and the metal part, and dissimilar metals in the electrically conductive environment. Surface grinding, heat treating, welding, cold working, forming, drilling, and shearing produce local or general changes on metal parts. These processing and fabrication operations also affect the susceptibility of metals to corrosion. The specific application determines the amount of metal that can be lost before a part is considered to have failed by corrosion. Some applications, where uniform general attack occurs, can tolerate a substantial reduction in the thickness of a part. In other applications, appearance is important, and the dissolution of a small amount of metal causes discoloration or contamination of whatever substance may come in contact with it. In food processing and storage, this is unacceptable. Mere discoloration of the food or the metal constitutes failure. Types of corrosion. Typical types of corrosion include general chemical attack, pitting, selective leaching, intergranular, selective attack on inclusions, concentration cell, crevice, differential temperature cell, and galvanic. Frequently, corrosion failures may be caused by the simultaneous action of two or more types. Atmospheric corrosion of metals by general chemical attack is the simplest and most common form of corrosion. In iron and steel, it is commonly called rust. White rust forms on zinc and aluminum. General corrosion occurs in the atmosphere, in liquids, and in soil, frequently under normal service conditions. The rate of attack can be rapid or slow. The metal surface can be clean or covered with corrosion products. It commonly occurs on metal surfaces having relatively homogeneous chemical composition and microstructure. Access to the metal by the attacking environment is generally unrestricted and uniform. Most metals are affected by general chemical attack in some environment. Steel rusts in the air, silver tarnishes, aluminum oxidizes, copper turns green. In some metals, such as steel, general corrosion produces a somewhat rough surface and removes a substantial amount of metal, which reacts with the environment and produces a loosely adherent porous coating of corrosion products. Other reactions, like the tarnishing of silver in air, produce thin, tightly adherent protective films, and the metal surface remains smooth. When investigating the effects of temperature on the corrosion of metals, the most important temperature to be checked exists at the metal corrodant interface. This temperature may not be the same as the temperature of the corrodant. A rise of 18 degrees Fahrenheit in the bulk temperature of a solution can increase the corrosion rate of unalloyed steel by a factor of 2 or more. In general, increasing the temperature increases the rate of corrosion. But even this general rule has exceptions. Steel is immediately attacked when immersed in water, but as the water temperature is raised, the oxygen content decreases, so the oxidation or corrosion of the steel decreases. Corrosion also decreases when a rise in temperature results in the formation of a thin protective film on the metal surface, or in passivating the metal. Every passive metal and alloy is susceptible to pitting, with the higher alloyed materials showing more propensity to pit than to corrode in a general manner. Pitting is extremely localized corrosion, and with very few exceptions, the pits are readily seen by visual examination and are generally sharply defined. The attack on the interior walls of the pit is reasonably uniform, but may be irregular when a secondary intergranular attack is introduced. Usually only a small overall weight loss occurs. Pitting begins when one area of a metal surface becomes anodic with respect to the surrounding surface. The combination of small anode area and large cathode area causes pits to form. Pitting also occurs when highly localized changes in the corrodant with the metal causes accelerated localized attack. This happens in crevices, for example. Other possible causes of pitting include local inhomogeneity on the metal surface, local loss of passivity, and mechanical or chemical rupture of a protective oxide coating. Sometimes a metal ion or oxygen concentration cell can form under a solid deposit. The most common causes of pitting in carbon steels are surface deposits that set up concentration cells. Also, dissolved halides can produce local anodes by rupturing the oxide films. If the external environment is aggressive or if a galvanic cell is active, pitting occurs at mechanical ruptures in protective organic coatings. Buried pipelines that fail because of corrosion originating on the outside surface usually fail by pitting corrosion. In stainless steels and other corrosion-resistant alloys, the most common cause of pitting corrosion is the highly localized destruction of passivity. This usually occurs in contact with moisture that contains halide ions and in particular chlorides. Selective leaching is also called parting corrosion. It is the removal of an element from an alloy by corrosion. The most common example of selective leaching is dezincification, the selective removal of zinc from brass, which is of course an alloy of zinc and copper. Many alloys are susceptible to selective leaching under certain conditions. The elements most resistant to the environment remain in the metal, provided a sufficiently continuous structure remains to prevent them from breaking away in small particles. When dezincification occurs in brasses, the zinc corrodes preferentially, leaving a porous residue of copper and corrosion products. Probably the second most often encountered type of selective leaching is the graphitic corrosion of gray cast iron. The graphite in gray iron is cathodic to iron and remains as a porous mass while the iron is leached out. Selective leaching does not occur in ductile and malleable irons because no electrically contiguous graphite network is present. Intergranular corrosion is the preferential dissolution of grain boundaries or the zones immediately adjacent to the grain boundaries. There is little or no attack on the main body of the metal grains themselves. In general, the grain boundary materials are more active chemically than the grains. This is because the boundaries represent areas of mismatch between the orderly and stable crystal lattice structures between the grains. Preferential attack is enhanced by segregation of specific elements or phases. Susceptibility to intergranular corrosion is usually related to thermal processing, such as welding. When the corrosion attack on the grain boundaries is severe, entire grains may be dislodged as the boundaries deteriorate. Certain austenitic steels are susceptible to intergranular corrosion. The susceptibility is called sensitization. Sensitization takes place when austenitic stainless steels are heated between 850 and 1550 degrees Fahrenheit. In this temperature range, chromium and carbon precipitate in the grain boundaries as chromium carbides. This generally happens when the carbon content of the stainless steel is above 0.03%, or if stainless steels are welded to carbon steels, or when contamination allows carbon to diffuse into the metal. The result is a metal with lowered chromium content in the area immediately adjacent to the grain boundaries, and thus a higher susceptibility to corrosion. In many corrosive environments, this chromium-depleted zone immediately adjacent to the grain boundary is rapidly attacked. Some ferritic stainless steels are also susceptible to carbide precipitation under similar but higher thermal conditions. Selective attack on inclusions is a special case of selective leaching. In this type of attack, the body of metal is resistant to the environment, and only small amounts of material are corroded away. Inclusions in the metal provide small anodic areas surrounded by large cathodic areas. Where the inclusions are in the form of elongated stringers and end grain is exposed to the environment, the attack is highly directional and deep penetration of the metal is possible. Inclusions may be present in many different metals. Usually they are accidental, but in many instances, various elements like sulfur, selenium, lead, and tellurium are added purposely to improve machinability. Free machining metals are invariably more susceptible to corrosion by selective attack. Concentration cell corrosion commonly occurs on metals buried in the ground. Metals corrode because they are in contact with soils that vary in chemical composition, water content, or degrees of aeration. The soil serves as an electrolyte, and when the concentration of one or more of the dissolved compounds or gases differs in the electrolyte, an electrical potential can exist. So when a piece of metal comes in contact with the two areas of differing potential, a concentration cell is formed. The portions of metal forming the anode are corroded away. This concentration cell form of corrosion also occurs when metals are immersed in solutions. The solution may vary in concentration owing to gases dissolved in the liquid. There may be a varying concentration of oxygen, for instance. When these different concentrations of solution contact different areas of the metal, a concentration cell is formed. Crevice corrosion. This is a type of concentration cell corrosion. The difference is that the corrosion develops from a crevice in a metal surface. Crevice corrosion can also develop at a joint between two metallic surfaces, between a metallic and a non-metallic surface, or beneath a particle or loose layer of solid matter on a metallic surface. These crevices create a difference between the concentration inside the crevice and outside. The result is an anode-cathode differential cell with electrical potential that causes accelerated attack. Crevice corrosion can progress very rapidly, tens to hundreds of times faster than the normal rate of general corrosion in the same environment. For example, a sheet of stainless steel can be corroded into two pieces by simply wrapping a rubber band around it and immersing the sheet in seawater or in dilute ferric chloride solution. The open surfaces pit slowly, but in the crevice under the rubber band, the metal is attacked rapidly, actually cutting into the steel as the corrosion progresses. This problem can be particularly serious in power boilers and in automobiles exposed to road salt in the wintertime. Thermal insulation can cause crevice corrosion. Once permeated by water, the insulation may act as a diffusion barrier to form a crevice and occasionally corrosion. Some insulations contain halides in sufficient quantities that repeated leaching by water can build up concentrations on the metal surface to levels sufficient for very serious corrosion. This buildup can be avoided by specifying thermal insulation with sodium silicate or some other corrosion inhibitor. Also, the halide content can be held to a very low level, or the leaching action can be prevented by coating the insulation with a waterproof compound or a metal jacket. In power generation equipment, crevice corrosion failures have occurred in main station condenser tubes cooled with seawater. These failures result from the formation of solid deposits on the tube wall and by marine organisms attaching to the tube. The failures have occurred particularly in condensers tubed with stainless steel. Crevice corrosion can also occur in riveted and bolted joints. Careful attention to design and assembly will avoid crevices. Uniform aeration and moderate but not excessive flow rates at the joints should also help avoid corrosion in crevices. The reactive liquids can be excluded by the use of primer paints or sealants. This is often used to prevent corrosion in bolted assemblies. A differential cell causing corrosion can be formed by a difference in temperature. This happens particularly when the temperature difference is sufficient to alter the level of dissolved oxygen from one location to another. The anode and cathode consist of the same metal and differ only in temperature. If the anode and cathode are areas on a single piece of metal, or they are on two electrically connected pieces of the same metal, immersed in the same electrolyte, corrosion proceeds as it will in any short-circuited galvanic cell. Galvanic corrosion occurs when certain dissimilar metals are electrically connected in an electrolyte. The less noble metal is attacked to a greater degree than if it were exposed alone. The more noble metal is attacked to a lesser degree than if it were exposed alone. The system is similar to an electric battery, generating electric current until the anodic metal is completely consumed by corrosion. This behavior is known as galvanic corrosion. It can often be recognized by the fact that the corrosion is more severe near the junction of the two metals than elsewhere on the metal surfaces. Galvanic corrosion usually is the result of poor design or material selection, or both. It can also be caused by a more noble metal in solution plating out on a less noble metal. One of the most disastrous types of failure by corrosion is caused by the selection of the wrong metals and combinations of metals for a particular application. The reason for the corrosion is, of course, simple galvanic attack, but the root cause is poor selection of materials. Summary: corrosion is electrochemical in nature. Oxidation occurs at the anode. Reduction occurs at the cathode. Passivity, the loss of chemical reactivity. Types of corrosion: general chemical attack, pitting, selective leaching, intergranular corrosion, selective attack on inclusions, concentration cell, crevice corrosion, differential temperature cell, and galvanic corrosion. The reactivity of metals. A galvanic series based on the reactivity of various metals in an electrolyte is generally a practical indication of the potential corrosion rate between different metals or alloys in contact with an electrolyte. An example is the galvanic series for seawater. Tables like this are often helpful in solving corrosion failures, as well as for selecting compatible metal combinations. In most electrolytes, the metals closer to the top of the chart are more active and will behave as anodes. Metals closer to the bottom, the noble end, will act as cathodes. The amount of separation between two metals in the chart roughly measures the difference in potential that can be expected. The separation is usually related to the rate of galvanic corrosion between the two metals in a given electrolyte. In most cases, metals from one group can be coupled with other metals from the same group without causing a substantial increase in the corrosion rate of the more active metal. Some alloys, most notably the stainless steels, can be either passive or active. Therefore, they may occupy two places in the galvanic series, a relatively noble position for the passive state and a less noble position for the active state. The passive protective barrier that makes such metals much less susceptible to further reaction is fairly stable over a wide range of oxidizing power. However, destruction of the film restores them to the active state. Thus, certain acids can be very harmful to an otherwise corrosion-resistant passive alloy. Organically coated or painted alloys are also sensitive to coating integrity. When metals of differing reactivity are assembled and coated, a small break in the coating of the anodic metal in the couple can result in an extremely rapid galvanic attack. If the coating is used to protect an active metal component of equipment in contact with a relatively large and passive metal component, the slightest void in the anode metal coating exposes it to rapid galvanic action with the relatively huge areas of cathodic metal. Rapid attack occurs even in a weakly conductive electrolyte. The thing to remember is that small anode to large cathode area creates extremely rapid galvanic attack, in effect an electrical stress concentration. And because of this, the cathode should be protectively coated, but not the anode. Imperfections or damage to a coating on the anode will create a small anode area in contact with a large cathode. Furthermore, if the anode is left uncoated, the anode area must be kept large relative to the cathode area. Corrosion can be aggravated by slow-moving and stagnant water. Low-velocity waters allow loosely adherent, solid corrosion products to form on metal surfaces. This creates crevice corrosion zones. Even the effectiveness of a corrosion inhibitor is reduced in a closed system where the water is stagnant or nearly so. On the other hand, swift-moving waters can also present corrosion problems. High-velocity water may sweep away the dissolved metal ions before they can precipitate as a protective passive layer. Also, any gritty solid suspended in swift-moving water can scour the metal, effectively removing protective layers and continually exposing fresh metal to corrosive attack. Impingement corrosion is a severe form of erosion corrosion. An impinging high-velocity stream of water can perforate tube walls rapidly. Sand, silt, or mud in the water will erode tubes severely. Most often, impingement corrosion is found in the elbows and turns of tubes or pipes. It generally manifests itself as deep, clean, horseshoe-shaped pits with deep undercut ends pointed in the direction of fluid flow. Impingement corrosion attack can also occur as the result of partial blockage of a tube, deflecting the main flow against the wall. In piping systems, the milder forms of erosion corrosion, as well as impingement erosion, can be reduced by increasing the diameter of the pipe. This decreases the velocity and turbulence. Frequently, small reductions in velocity can greatly reduce the rate of metal removal. The streamlining of bends is also useful in minimizing the effects of impingement. If possible, inlet pipes should not be directed onto the vessel walls. Flared tubing can be used to reduce problems at the inlet tubes in a tube bundle. Biological organisms have some effect on the corrosion processes of metals. Bacteria, algae, and barnacles can directly influence anodic and cathodic reactions. They affect protective surface films by producing corrosive substances and solid deposits. Marine organisms such as barnacles and mussels attach themselves to surfaces, grow, and effectively seal off a small part of the metal surface from its environment. This is called fouling or biofouling. Concentration cells form beneath the barnacles and produce deep pits. As long as there is some relative motion between the metal and the water, these organisms can be discouraged from attaching themselves. Rapidly moving vessels accumulate only small quantities of organisms. The major fouling occurs when the vessel is docked. Heat exchangers using seawater as a coolant suffer from biofouling. During shutdown for maintenance, the sea organisms attach themselves and eventually cause corrosion. Fouling by marine organisms is inhibited most effectively by anti-fouling paints. These paints contain toxic substances, usually copper compounds. They function by slowly releasing copper ions into the aqueous environment, poisoning the mussels, barnacles, and other creatures. The major factors influencing the corrosion of uncoated metal components buried in the soil include soil composition, oxygen and carbon dioxide content, electrical resistance, bacteria, and stray current. Soils that contain organic acids, such as those derived from humus, are relatively corrosive to steel, zinc, lead, and copper. The measured total acidity of an acidic soil appears to be a better index of its corrosivity than pH alone. High concentrations of sodium chloride and sodium sulfate in poorly drained soil make the soil very corrosive. Some of the most corrosive soils encountered are backfill soils containing cinders or ash. Chemical pollution from leaks or spills often results in very aggressive corrosion of metallic objects like pipe and underground structures. Zinc coatings are surprisingly effective in reducing weight loss and pitting rates in steel exposed to soils. A major source of protection appears to result from the alloy layer formed between zinc and the steel surface in hot dip galvanizing. The threads in steel pipe often fail by galvanic corrosion where they are connected to brass valves. Couplings should always be insulated whenever wide variations in metal composition exist. Zinc coatings or replaceable zinc or magnesium anodes are also protective, but they deteriorate more rapidly when galvanically coupled to large areas of bare iron, steel, or copper. In these cases, insulating coupling should be used. A wide variety of coating methods and cathodic protection devices are available to help prevent corrosion in buried pipelines and tanks. As a general rule, the use of coatings on buried structures without cathodic protection is not recommended. As a matter of fact, in aggressive soils where microbiological corrosion occurs or where stray currents are encountered, coated structures frequently experience shorter life than uncoated structures. This is due to accelerated attack at the points of coating breakdown. A fairly effective method of providing protection for buried metals at reasonable cost is to use thick coatings of coal tar with reinforcing pigments or inorganic fibers which reduce cold flow. The coatings are used along with properly designed and installed cathodic protection systems. Atmospheric corrosion, like all other forms of corrosion, occurs in the presence of an electrolyte. The metals ordinarily used in equipment and structures corrode at a negligible rate when exposed to atmosphere without moisture to serve as an electrolyte. For example, obsolete aircraft and other metal parts exposed in the desert air remain free from corrosion for long periods of time. And metal parts exposed to air at temperatures below the freezing point of water do not corrode to any significant extent, because ice is a poor electrolytic conductor. One factor that accounts for many of the differences in corrosion rates is the formation of corrosion product films that provide various degrees of protection. Lead is equally resistant to rural, industrial, and marine atmospheres because lead readily forms tightly adherent, insoluble, highly protective films in the air. These protective films consist mainly of oxycarbonates, but contain equally protective sulfates and oxychloride in marine and industrial atmospheres. Rural atmospheres are generally free from particulate matter and corrosive gases. This accounts for the low corrosion rates. Industrial atmospheres, however, contain dust of carbon particles and carbon compounds, metal oxides, metal salts, and sulfur dioxide. With moisture, the dust particles bearing soluble contaminants produce corrosion by forming differential aeration cells and other types of concentration cells. At and near the seacoast, saltwater spray is the most corrosive element. The rate of attack on exposed metals varies widely, depending on distance from the ocean, prevailing wind direction, and relative humidity and temperature fluctuations that produce condensation. In marine atmospheres, protective films can be penetrated by chloride ions. The high solubility and hygroscopic nature of metal chlorides cause rapid corrosion on carbon and low alloy steels. Zinc and cadmium plating extend the life of steel hardware to a useful but limited extent. Large steel structures must be protected by painting. When a corrosion failure occurs, several corrective methods are available to prevent or at least minimize future failures. Very often more than one method is used at the same time. The more important corrective and preventative measures are change in alloy, heat treatment, or product form, use of resinous and inorganic-based coatings, use of inert lubricants, use of electrolytic and chemical coatings and surface treatments, use of metallic coatings, use of galvanic protection, design changes for corrosion control, use of inhibitors, changes in pH and applied potential, and continuous monitoring of variables. Where the environment cannot be changed, a change in alloy, heat treatment, or product form is generally required. Under some circumstances, both alloy and product form may be changed. Solution annealing of austenitic stainless steels minimizes the risk of intergranular attack and stress corrosion cracking. For stainless steel weldments that cannot be annealed, when intergranular corrosion or intergranular stress corrosion cracking is of concern, A quenching procedure can be used. If the quenching procedures prove ineffective, either a low-carbon or a stabilized stainless steel may be substituted, depending on the mechanical property requirements. Many coatings and lubricants are available for corrosion protection. These include acrylics, epoxies, phenolic, furanes, and urethane. They are used extensively for corrosion protection in the form of paints, potting compounds, adhesives, coatings, and linings. Their chemical resistance makes them suitable for many applications. A wide variety of metallic coatings are applied, mainly by electroplating, hot dipping, electrolysis processes, and cladding. Also used are selective brush plating, spray metallizing, vacuum deposition, gas plating, and cathode sputtering. Selection of a coating process is based on the availability of equipment, criticality of the particular part, and the overall cost of the protection needed. Certain chemically inert resins can sometimes serve as both effective lubricants and as corrosion-resistant coatings and linings. These include silicones, esters, and fluorocarbons. In seacoast environments, lubricants must frequently perform this dual role of lubrication and corrosion protection. Aluminum and aluminum alloys can be anodized to provide effective protection in natural environments. Anodizing is not effective against aggressive environments, especially those that are acidic or alkaline. Most aluminum components for aircraft applications are anodized for added corrosion protection. The anodic coating also serves as an excellent paint base. The sulfuric acid method should not be used on assemblies that can entrap liquids. Instead, the chromic acid method must be used. When electrolytic processes like anodizing cannot be used, chromate-type chemical conversion coatings are often used. Stainless steels often show rust spots on the surface after exposure to humid conditions. The rust is from small particles or ordinary iron or steel embedded in the stainless during cutting, machining, fabrication, and handling. A common source of iron particles is the residue smeared on the surface during wire brushing. Pickling involves the removal of these iron or steel particles. Removing the particles allows a very thin but highly effective, complete passive film to form on the stainless steel surface upon exposure to a clean, dry atmosphere. Cathodic protection may be applied by either impressed direct current or sacrificial anode. In the impressed direct current type, the structure to be protected is made the cathode of a direct current electrical circuit. The anode in the circuit is an auxiliary electrode, usually iron or graphite, located some distance away. Current flows from the electrode through the electrolyte to the structure. It does not corrode. In the sacrificial anode system, the structure to be protected is made the cathode in a galvanic corrosion cell. Current is supplied by the corrosion of anodes commonly made of zinc or magnesium. Voltage and current are limited by the corrosion of these sacrificial anodes, and periodic replacement is required. Some metals can be prevented from corroding in an electrolyte that might otherwise attack them. The technique is called Anodic protection and involves an external potential, but it is applicable only to metals and alloys that show active-passive behavior. Anodic protection has been applied mostly to steel and stainless steel. Summary: factors affecting corrosion. Passivity, anode to cathode area, slow-moving and stagnant water, impingement, biofouling, acid soils, corrosion prevention and correction, coatings and paints, corrosion product films, cathodic protection devices, sacrificial anode, and anodic protection. Stress corrosion cracking. Stress corrosion cracking is a mechanical environmental failure process in which sustained tensile stresses and chemical attack combine to initiate and propagate fracture in a metal part. Failure takes place in less time than it would from the separate effects of the tensile stress and the corrosive environment if simply added together. Therefore, correction and prevention of stress corrosion cracking will involve eliminating the stresses, which are often residual, or the exclusion of the corrosive environment. Principal sources of tensile residual stresses during manufacture occur from thermal effects, such as those encountered in welding, casting, and heat treating. Cold forming and the assembly of parts can also create tensile residual stresses. Other sources include improper heat treating practices, such as failure to preheat when required, overheating during austenitizing or solution treating, failure to provide required temperature uniformity in furnaces, use of quenching practices too severe for a specific alloy or part shape, and undue delay in transferring workpieces from the quenchant to the tempering furnace. Tensile residual stresses that are damaging or potentially damaging in conjunction with environment attack are produced in many different types of surface finishing treatments. These treatments include electroplating, electrical discharge machining, and under some conditions, conventional grinding and machining. Cold forming or fit-up and assembly stresses also generate harmful residual stresses. When hydrogen is produced in the finishing process and diffuses into the metal, internal stresses can be developed by the formation of pockets of hydrogen or methane. Shot peening and surface rolling are often used to produce beneficial residual compressive stresses in metal surfaces. These stresses can retard stress corrosion cracking. However, the magnitude of compressive residual stress imposed by shot peening must be great enough to overcome the effects of local tensile residual stresses. Metal parts and assemblies are designed to withstand certain stresses, but additional stresses can be introduced in service in various ways. The combined effect of stress raisers and environment create mechanical environmental processes conducive to failure. A major source of stress in service is the exposure of metal parts to high and low temperatures when the fluctuations are accompanied by non-uniform heating rates and sharp thermal gradients. The general distribution of the thermal stress results in extensive cracking and sometimes complete fragmentation. In many metals, cyclic stresses in combination with residual stresses and corrosion can result in substantially reduced fatigue strength and service life. The effect of stress direction on stress corrosion cracking is dramatically shown in this micrograph of a Type 316 stainless steel bellows. In service as an expansion joint in an underground pressurized steam line, it was operated at about 325 degrees Fahrenheit. The exterior of the bellows had been exposed to rainwater in soil containing corrosive chemicals, probably chlorides. The stress corrosion cracks originated in the outer wall surface, propagating about midway across the wall. At midwall, the crack encountered a neutral of compressive stress. The crack turned 90 degrees in both directions and continued parallel to the curve of the bellows. Since the inner surface was in compression, the SCC did not propagate through the wall. Other parts of the bellows were exposed to the soil water, but these areas were in compression or neutral and did not crack. The area in tension was exposed only to steam and thus could not crack. The initiation site of a stress corrosion crack may be submicroscopic and determined by local differences in metal composition, protective film thickness, corrodant concentration, and stress concentrations. A pre-existing mechanical crack or other surface discontinuity may act as a stress raiser and thus serve as a site for initiation of stress corrosion cracking. Stress corrosion cracks ordinarily undergo extensive branching, especially at the crack tip. They proceed in a general direction perpendicular to the stresses contributing to their initiation and propagation. Macroscopically, fractures produced by stress corrosion cracking always appear brittle They exhibit little or no ductility, even in very tough materials. In this way, they resemble corrosion fatigue fractures. Most stress corrosion cracks exhibit changing fracture planes as they propagate, producing faceted intergranular rupture. The surfaces of fractures from stress corrosion cracking usually contain easily identifiable regions. These are regions of crack initiations, slow crack propagation, and final rupture. Final rupture usually occurs by tensile overload. Thus, the final fracture area often shows some evidence of ductility, a shear lip or a herringbone pattern emanating from the slow cracking zone. The areas of slow crack growth are often stained or discolored, more so than the area of final fast fracture. However, the presence of staining or corrosion products on the fracture surface is by no means positive proof of stress corrosion cracking. Some stress corrosion cracking fractures are not stained or discolored, especially in materials with good corrosion resistance. In addition, many fractures become corroded before inspection can be accomplished. The slow propagation zones of stress corrosion cracking are usually much rougher in appearance than those of corrosion fatigue cracks. They do not contain fatigue beach marks or macroscopic evidence of cold work. But the fractures from both stress corrosion cracking and corrosion fatigue can and often do initiate at corrosion pits or other stress razors on the surface of the part. Fractures caused by either of these mechanisms always initiate at the part's surface or at some location where the aggressive chemicals or environment can contact the metal. By corollary, if the crack is found to have subsurface origin, corrosion fatigue and stress corrosion cracking can usually be eliminated as possible causes of failure. Stress corrosion cracking frequently occurs in commercial grades of low carbon steels, high strength steels, austenitic stainless steels, and other austenitic alloys, high strength aluminum alloys, brasses, and certain other copper alloys. High purity metals generally are much less susceptible to stress corrosion cracking. However, every metal will stress corrosion crack in at least one environment. As a rule, any metal with a small grain size is less susceptible to stress corrosion cracking than its larger grain counterpart. Elongated grain structures, characteristic of high-strength wrought aluminum alloy mill products, markedly affect the path of stress corrosion cracking in susceptible alloys and tempers, especially in the short transverse grain direction. Stress corrosion cracking is often caused by specific ions present as impurities in the environment. For example, even in the solution heat-treated or annealed condition, austenitic stainless steels at 390 degrees Fahrenheit crack in aqueous solutions containing as little as 2 parts per million of chloride. Sensitized austenitic stainless steels crack at room temperature in water containing about 100 parts per million of chloride or 2 parts per million of fluoride. Some copper alloys crack in environments that contain similarly low concentrations of ammonia. Analysis of corrosion failure. Complete investigations of corrosion failures can be very complex, but not all corrosion failures require a comprehensive, detailed failure analysis. The preliminary examination will often determine the extent of investigation required. In general, the investigator should consider various possibilities without being costly or time-consuming. Very important are routine checks to determine if the specified material is used. Such checks have shown that so-called seamless tubes that split longitudinally in service were actually welded tubes that corroded preferentially at the welds. Forgings that failed in service were actually castings. Failure was initiated by corrosion at the porous areas exposed at the surface of the metal. In the investigation of corrosion failures, knowledge of a part and its application is desirable. Accurate history is especially important. In this regard, the type of environment whether continuous or intermittent, or any part or process changes should be particularly noted. On-site examination is generally the same for corrosion failures as for other types of failure. The region of failure itself should be examined visually using hand magnifiers and any available viewing equipment. If possible, the failed component and related components of the system should be photographed before samples are removed. Color photographs are highly desirable, especially when colored products of corrosion are present. When on-site sampling is done, the investigator should be guided by the history of the failure. The bulk environment to which the failed part was exposed should be sampled. Suitable techniques should be used to obtain samples and make observations on the local environment at the point of failure. Samples from adjacent areas and apparently non-corroded regions should be obtained for comparison purposes. New or unused parts can provide evidence of the initial or unexposed condition of the part. If abrasive cutoff wheels must be used, only non-contaminating cutting coolants should be used. The preliminary laboratory examination will vary depending upon whether or not an on-site examination was done and its completeness. An on-site examination by a well-equipped investigator will include much of the work that might be done in the lab. Samples should be handled so that maximum information can be gained before any sample is damaged, destroyed, or contaminated. Also, a complete written and photographic record should be kept through all investigation stages. The sample is first examined visually, usually with the aid of a low-power magnifier. At this stage, important features include the extent of damage, general appearance of the damage zone, and the color, texture, and quantity of surface residues. If substantial amounts of foreign matter are visible, cleaning is necessary before further examination. Both light microscopy and electron microscopy can be used to observe minute features on corroded surfaces, to evaluate microstructure of the metallic parts, and to observe the manner and extent to which the metal was attacked by the corrodant. Viewing the clean surface with a stereo microscope clearly shows gross topographic features, pitting, cracking, or surface patterns that can provide information about the failure mechanism. This information includes whether corrosion was the sole phenomenon involved, the type of corrosion, and whether other mechanisms such as wear and fracture were also operative. The job of the failure analyst is to establish what role, if any, the corrosion products play in the failure, to identify and analyze the metals, the environment, the inhomogeneities in the part's surface, and the foreign matter on the metal surfaces. Ordinarily, the purpose is not to look for minor deviations in the chemical composition specified for the part, but rather to check for possible major deviations. The object is to make sure the correct alloy was used. However, for some austenitic stainless steels, the corrosion resistance and other properties of welded joints require close control over the composition of the stainless steel and the weld metal. Some laboratory test methods have been accepted as standard by both the military and industry. To shorten testing time, corrosion is accelerated in relation to naturally occurring corrosion, usually by increasing temperature or by using a more aggressive environment. However, because various factors influence natural corrosion processes and differ widely in time dependence, the results of laboratory tests must be interpreted carefully. Tests can be related to expected service behavior only when close correlation with long-term service results has been established.